This is a basic introduction to sets, and set theory is a big piece of mathematics. Has to do with how we organize groups of things, whether they're numbers or other things. A set is just a collection of objects. Like I said, those numbers or those objects could be numbers, or they could be other things. They could be anything that you could list. We can then put into a set, okay, and then describe those sets. An element is what we call, or sometimes an entry, or what we call the values that are in a set. So when we talk about the elements of the natural numbers, we're talking about all of the numbers that are in that set of natural numbers, okay? Before we talk about sets in general, I want to talk a little bit about the ways that we classify numbers, okay? So in all of the numbers, so it's kind of like we have a big giant box. Inside this box is the universal set of all numbers. And then we have this organizational chart that's actually called a Venn diagram, which will be talked about more in later sections here. Okay, a Venn diagram that uses basically bubbles to show how groups interact. So for example, the fact that this natural number bubble is entirely inside the whole number bubble means that every value that is an element of the natural numbers, and we can see here that's 1, 2, 3, etc., is also a whole number because all of the natural numbers are contained in the set of whole numbers, okay? All right, so starting there, we have the natural numbers, which are also called counting numbers. Okay, I'm going to move that over here. So we can also call those counting numbers. Okay, and then the whole numbers are the counting numbers plus 0. So we've added one more entry into the whole numbers, and that is the 0. Okay. This is the one number that distinguishes whole numbers from natural numbers, okay? All natural numbers are whole numbers, but not all whole numbers are natural numbers because of the 0, okay? And the next bubble moving outward is integers, okay? And integers are numbers that can be positive or negative or 0 and are whole numbers, okay? So we have all of the numbers inside whole numbers, which would be 0, 1, 2, 3, 4, etc., as far as we can go. But we also need to add -1, -2, -3, -4, -5, etc., all the way down the other direction, okay? So all of these sets are infinite. There's an infinite number of values that go into each of these. But the set of integers is bigger than the set of whole numbers because we add all of the negative whole numbers as well, or I should say negative natural numbers, okay? And then moving out a little bit further, we have rational numbers, okay? And rational numbers are sometimes defined a little bit differently, but a rational number is a number that can be written as a fraction of integers. So remember what an integer is. It's a whole number. It doesn't have any decimal or fractional part to it. But a rational number then is a number that can be written as those. So -9/2, okay, is a rational number because -9 and +2 are both integers, all right? Now, -9/2 could also be written as -4.5. So even if we see it as -4.5, it is still a rational number because it can be written as a fraction of integers, okay? And if we look at these other examples here, 7.12, anytime we have a repeating decimal, that is something that we can write as a fraction. 0.12, and I'll just go ahead and show you how we would do this. We would write it as 7 and 12/99, and then we could reduce that and combine it and write it as a single integer on the numerator and denominator if we want, whatever 99 times 7 is, and then add that to 12, okay? So we could write it then as a fraction of integers, okay? So any repeating decimal can be written as a fraction of integers, so it's rational. Also, this is called terminating decimal, okay? Any decimal that has a definite end. So 11.23 stops at the 3. It's not 23 something something something, okay? It's 11.23, and so we could write that one as, I'll come down here, we could write that as 11 plus 23 hundredths, and then we could go ahead and combine that. We could do 100 times 11 plus 23 to get a single value, single integer in the numerator as well. Okay, so anything that terminates can also be written as a fraction of integers, so it is also rational. And then again, 3/4, both of those are integers already, so that's already in its rational notation. Okay, and then outside the rational numbers, this box is all of the real numbers, and it's not labeled on here, so I'm going to add that. But this is all of the real numbers. There are such things as complex numbers, which include an imaginary part. If you think about the square root of -1 or the square root of negative anything, that doesn't exist. So those go into what are called the complex numbers, which we're not going to be dealing with here, but those are outside the reals. Okay, so we're only dealing with real numbers. And then the other bubble that's over here to the right is irrational. Okay, and if we defined rational as numbers that can be written as a fraction of integers, irrational is just numbers that cannot be written as a fraction of integers. Okay, so for example, this number right here, 2.7182818281. Okay, so and maybe kind of hard to see, but that is actually the approximation for what's called E, or Euler's number, or Euler's notation. But that is a number that is irrational because it does look kind of like it's going to repeat, but it really doesn't. It doesn't repeat and it doesn't terminate. It's a decimal that goes forever with no pattern, so it is irrational. Okay. Two more examples of that are root 2. Okay, square root of 2 does not exist as an integer or even a rational, like a fraction. And then same thing with pi. We usually approximate pi at 3.14, but as you likely know, pi actually continues forever and does not repeat. Currently, I think mathematicians have found something like 200 million digits of pi and have yet to find a pattern or an end. So that's something that is fun for mathematicians to try and find, but not necessarily super useful. So that is another example of an irrational number. Okay? All right, so again, we're talking about sets, but these terms will come up as you're going through some of the practice problems and in the notes. So I want to make sure everyone understands what each of these terms mean. So if I say integer, we know that I'm talking about the positive or negative whole numbers. Okay? All right. Sets can be described 3 different ways. They can be written verbally, so we could say the set of even numbers less than, or even whole numbers less than 10, or something like that. We can also write them as a list, and frequently when we write them with a list or in set builder notation, we're going to see braces, which are the curly brackets, okay, these things. So we might have a list of, I'll go ahead and do the, what did I say, even integers less than 10, so that would be 2, 4, 6, and 8, okay? So that would be an example of a list notation for even integers less than 10, okay? And then set builder notation also has the braces, but the way that we write this is we start with the brace, and so we say the set of, and then usually there's a variable here. X is a really common one, so I'm going to say X, and then we'll see a vertical line. Sometimes the words such that are written out, but usually it's a vertical line, and it means such that. Okay, so it's the set of X such that X, and then some kind of description that tells us what applies to the values in this set. So X is an even integer less than 10. Whoops, 10. Okay? And we do have some other symbols that you may see. The symbol for integer is a script Z, okay? So if you see a capital Z or kind of maybe like a curly-ish Z, then it's talking about all of the integers. Okay, so it's the set of X such that X is an even integer less than 10, okay? Now and one more thing about these sets, it does not matter when they are listed. It does not matter the order we list them in. So the set 2468 is exactly the same as the set 6428. Okay? All right, one more important set that we always need to take into consideration is the empty or null set. There's 2 different notations for this. We might see braces that are empty and have nothing inside them. Okay? Or we might see a big O with a slash through it, okay? And I know that some of us might be in a habit of writing our zeros with a slash through them to indicate that it's not the letter O, but really, I strongly encourage you to break that habit, because if you put a slash through it, that means something entirely different from zero, okay? So this is not a zero, okay? Zero is a number, it is a whole number, it is an integer, it is a rational number, it is a real number, it is all of those things. The empty set says there are no values that satisfy whatever our condition is, or there are no values in the set. So those are definitely different, so just be careful with zeros, okay? Zero kind of gets a bad rap as not being a real number, but it definitely is, okay? All right, and one more thing about the empty and null set, we do not want to write, draw a line here, we do not want to write this, okay, because that means the set of the empty set, which doesn't really make sense because now there's an entry inside the set, so just don't do that. Okay, so here's a couple examples with sets. Here it says we're giving them in list notation. So the first one asks for the integers between -6 and 2, and be careful about words like between. If we have between two values, that does not include the ends. So we are not including -6 and 2. So in other words, this is exclusive. Okay, if it said the integers from -6 to 2, then we would include -6 and 2. But in this case, between means don't count those, okay? So this is going to be, I'll come over here, this is going to be the set of, and then we're doing integers, so those are all the positive or negative whole numbers. And so we have -5, -4, -3, -2, -1, 0, and 1. Okay, again, I did not include 2. And I listed these in numeric order. That's not necessary. Like I said, the order does not matter when we have a list of elements in a set, but usually just for organization purposes, it's nice to have a set that's listed in order so we can make sure that we get everything, especially if we had 12 different entries in a list. It might be harder to keep track of whether or not we included all of the necessary ones if they weren't in order, okay? All right, and then for part B here, we have the set of X such that X is a vowel in the English alphabet, okay? So here we're listing a set of vowels, which are going to be A, E, I, O, and U. So here we do not have numbers, we have letters instead, but that's okay because remember we can have anything that we want, any objects or values as elements in our set. Okay, two more symbols here that we need to know. This one that kind of looks like a C with a line through the middle or kind of like a little tiny E represents is an element of. Okay, so if we see that, let's take for example part B up above. We know that the letter U is in that set, so we can say that U is an element of set here, and I guess I need to name this. Okay, time out here. Let's call this set V. Okay, sets are frequently labeled with capital letters the same way sequences are. So we'll call this set V for vowel. And so I'm going to say U is an element of V, okay? Or it could be written just without the label at all. U is an element of A, E, I, O, U. And I could write out the whole set there. But so that symbol, okay, that symbol right here means, whoops. Oh, I hope that didn't move too much. Okay, means is an element of or is in the set of, okay? And so then the second symbol, fairly intuitive if we think about like equals or not equal to, whenever there's a slash through a symbol in math, that means not, okay? So this right here means is not an element of. Oops, sorry. Is not an element of. So for example, I know that the letter M is not a vowel, so I can say that M is not an element of set V, capital V, okay? All right, next thing here is cardinality. Another term we need to know, cardinality means the number of elements that are in a set, and the notation for a set's cardinality is n and then in parentheses a. So think of that as the number of elements of A, okay? And then if a set's cardinality is a whole number, then the set is finite. So if n of A equals 4 or 37 or 900,327, something like that, then it is going to be a finite set. Even though that's a large number, it's still finite because we have a discrete number of values. We can count all of them, okay? If it does not have a whole number as its cardinality, okay, and by the way, 0 does count. The null set is a set, and then the cardinality would be 0, okay? If it does not have a whole number, okay, if we can't count the number of terms in the set, then it is considered infinite. So in other words, we have an infinite number or an unlimited number of terms or entries into our set, okay? And then another term here, two sets are equal. Okay, two sets are equal if they contain exactly the same elements. So if everything in A is in B, and if every element of B is in A, then A and B are equal. Okay? All right, so here we've got a couple examples looking at whether or not sets are equal. First, we have the set of A, C, E, F, and then we have the set X such that X is a letter in the word face. Because those are the same thing, again, order does not matter, then yes, these are equal. Okay? And then for the last example, we have the set 2, 4, 6, 8 that's listed, and then we also have the set 0, 2, 4, 6, 8. These are not equal. Okay? And the reason that they are not equal is because the second set includes a 0, the first set does not. Again, 0 is different from the empty or null set. We can't just say, well, 0 isn't anything, so it doesn't count. But it really does. It makes a difference. It is an entry in this, or an element of the second set and not the first. So it does disqualify the two sets from being equal.